Day 2. Interesting and full program, starting with the maybe fundamental properties of hydro-treating catalysts in modern systems. And then towards the end, we have several interesting contributions dealing with the very important problem of catalyst deactivation and changes during use. So the first presentation we'll hear is a joint presentation. Is that you?
No, it's this one. They moved this one.
So it's a joint presentation from the University of Delft and University of Munich.
No, you can just put it back where it
It's
was.
authored by B. Müller, Van Langeveld, Jacob Moulijn, and Helmut Pötzinger, and the presentation will be given by Jacob Moulijn. I won't take time off to read off the long title.
Do it myself.
Really a lot of feedback today here already.
This one.
I think this one.
It's this one.
That one.
They can move this one over there.
Cooperation, as was told by the chairman, between the University of München, that's the group Hans Kneuziger and our group. In fact, the PhD student is Barbara Müller, and she is not here. My co-worker Dick van Langeveld is not here. Helmut Kneuziger is here. He could have presented a lecture. We had to make a decision, and I'm doing it now. The subject is characterization of sulfided molybdenum aluminum catalyst by TPR and transmission infrared spectroscopy of adsorbed CO. In fact, there are several aims of our investigation, and also a very fundamental one. Is there a molecule that's very useful to use as a probe molecule? We had the impression that perhaps NO2 are not the most ideal because they are reactive. We want to have a more soft molecule. So it was also the aim to see if such a thing could. And also what we want to do, that was the major aim, of course, when you apply texture program techniques, you have very global information, broad peaks, and then when you want to have structural information, you should also use, of course, spectroscopy. But it's not so simple. Sulfides is not simple in spectroscopy. So we wanted to know if this was a good setup. But I come back to it a little bit later, of course. First I'll discuss the TPR equipment, the principle. I'll give one result, and then I give a fact, let's say 6 spectra, 8 spectra, so it will not be too much information after dinner. Eh? Well, it doesn't matter. I can do without pointer.
Point of the view, rather.
Probably will overlook.
Yeah, well, you can point at the
okay.
in the meantime, but I'll try to find it.
Okay, what the instrument is, in fact, it's a TPR instrument, a little bit more complex. What we first do, we have got a reactor here, and we can sulfide an H2S, H2 mixture that goes then through the reactor, so you can carry out temperature program sulfiding. We started that work, I believe, in the early 80s, and we have always left it, so we're still doing it, temperature program sulfide. And then you have a controlled way of transformation of the oxidic phase into the sulfided phase. And we do it by basically following the product, so that's here H2S, which is a UV detector. We start with a mass spectrometer in the beginning, but UV is better. And then after trapping, we measure the H2. So you have both the products, the H2 consumption and the H2S production. And then the FAD is just for when you have carbon. Then when we have sulfided, we can then do, we can stop the sulfiding, cool down, and then do a TPR. program. What we did here, to make sure that you follow it easily, I put the temperature program here plus the gas phase. We did a sulfiding program by heating an H2S H2 mixture with 10 K per minute up till 400 degrees C. And then we stopped, had 1 hour continued sulfiding, switched to argon usually, and then you sweep off a lot of H2S, and we cool down in argon, and we start the TPR program. I have not taken with me typical TPS, temperature program sulfiding patterns that apply to the beginning, but to give you the message for molybdenum, what you do find is a few important observations you make. The first one is sulfiding of molybdenum is very easy. Most of it already happens at between room temperature and 50 degrees C. And when you sulfide further, you go in principle to about MoS2, and then there is some breakage of the molybdenum sulfur bond, or perhaps it's hydrogenated, and you go then back to MoS2. And the mechanism of oxygen sulfur exchange. But again, in molybdenum case, nearly in all cases, the sulfiding is very easy. When you compare sulfiding this reduction, there is a window of several hundreds of degrees C as difference. So the reduction is much more different. So the oxygen sulfur exchange is an easy step. Of course, when you, for instance, are sulfiding cobalt alumina, then you have things like solid state diffusion. And then it's not easy. For instance, when you have cobalt aluminate, you can only sulfide it at typically, let's say 700 degrees C, because the cobalt has to migrate through the salt. And then you have another rate determining step. But even then, the sulfiding step itself is very fast. So that's the observation. It's also critical how you do this here. This looks so easy, the argon line in green. But when you switch to another gas composition, a very complex chemistry can go on. When you switch, it could even be that H2S stays behind, that you have H2S dissociation, and that you have more sulfur when you cool down argon than when you cool down an H2S phase. Can be, depends on the system. We did do this for transition metals very general, of course molybdenum, tungsten, cobalt, nickel, but also ruthenium, platinum. And then you find that phenomenon that's rather complex, but one phenomenon I come back to, you find in all cases, and that's the case, the point of the excess sulfur, or the reactive sulfur. I now confine myself to molybdenum, so we did do here the TPS. We assured that we did have them basically sulfided all molybdenum, because again it's an easy reaction. Okay, then to give them one example, and I shall go in some detail on it, of course. That's the TPR of sulfided molybdenum alumina. And what you see here, this is the H2S signal, the production, of course, in TPR, and here is the H2 consumption. You see there an orange peak, that's the H2S desorption. Again, that peak strictly depends on the way how you flush and what temperature you do it. So you can have to, or you don't. It depends on the preheat. It's not fundamental. You see this very nicely that to me, I'm sure it's absorbed H2S because there isn't any H2 consumption involved. So the comparison of the two signals gives you a lot of information. Then you see the peak given in red, and you see there both an H2S production and H2 consumption. And then you continue, the green one you see H2S, it's a very broad peak of course. You see the H2S production and only a very limited H2 consumption. The calibration factors are about equal in the two cases, not completely. And the blue one here, we have here MoS2, again H2S production, H2 consumption. Okay, also interpretation. Now part of it we are pretty sure of. Desorption is logical. The green one certainly is a H2S production without adding hydrogen. So this immediately shows that you have here hydrogen in the system. Yesterday, Nan Topside, for instance, she gave evidence for SH groups, and she lists, I believe, 4 techniques: NMR, infrared, Raman, I believe a 4th one. But you see that very easily with this TPR technique. You see also what you have as. Oh, thank you. Now the only point that it loses. It is, yeah.
You got it backwards.
I can see it myself, but you perhaps not. Yeah, but okay. You see it anyway, but you see is that in this TPR technique, you see very easily that you certainly have SH groups, and although you don't have structural information, you certainly know how much you have. And that's also a typical characteristic of these techniques, of these temperature program techniques. They're a little bit blind techniques, you might say, but so you have species, but you know exactly how many species you have. And you have a lot of H. You can, it depends, of course, on the system. You could go and discuss it if you want to know. Then this one, I'm now pointing to the higher temperature. That one is very easy to understand. When you make a thermodynamic calculation, then you write down the reaction MoS2 plus H2 gives 2H2S. You can calculate where this line should be under equilibrium. You have to allow that, of course, for some mass transfer calculation. That's not so difficult. And it's exactly thermodynamically determined H2S production. Also, this sulfur, of course, is not interesting in HDS. It's very stable, so it's always there. Then we come back to the red peak, and all that has intrigued us very much, and even it took us some time before we have published it because we were not so sure what to say about it. We published in 1990 in Journal Catalysis, I believe, and Applied Catalysis. But you see here you have a very reactive sulfur, and it reacts 1-to-1 about, within, let's say, 10-15%, depends on the system. And it's very interesting because this sulfur, what you find here, that could be a measure of the sulfur vacancies during the reaction, because during the reaction, this peak will disappear. So we are sure that, or we find that it's very interesting to know what's happening there. It could be that they're active sites. Anyway, you see you have the different species of sulfur, you want to know what it is, of course. We tried a lot of things. For instance, we tried much power spectroscopy, but we find nothing here when you change this. You don't find it back. We tried other techniques. In electron microscopy, you see nothing, of course. Or you have to be very careful, perhaps, but we couldn't do it. So we couldn't find the technique. XPS we tried, we found nothing. And then we turned, of course, to our colleague in München, and we discussed, could you do a chemisorption method? And so what we did do, we took the system here, and we did here CO chemisorption, and then we reduced that CO chemisorption, and also here, to see also if you could find back these. Okay, so that's again so it's clear, I guess, now from 4 types of sulfur. 2 we are sure about, and 2 not, and we would like to know what it is. And for instance here, what would you expect here in the green area? When you would have condensation of neighboring SH groups, you would expect molybdenum 4+. Of course, in principle that will be as in the most simple situation. So the MbCO chemisorption, you might see molybdenum 4+. I'll show you it's not that easy. Here in this case, you expect, we have called it chemisorption sulfur on lower valency sites, lower oxidation sites. It could be, as far as we are concerned, molybdenum below 6, but what? Can you see that? And you will see that that very nicely shows up. Now I skip a little bit to I still want to show again the same picture to make sure that I make myself clear. What we will do, we mimic this procedure in München as close as possible. You can't do it, of course, in an infrared cell in the same way. So we hydrogenate about 315K, that was pretreatment, and then we expect that we only remove the adsorbed H2S. In principle, it could be a little bit, sometimes you find perhaps a little bit of H2S still. But there's no reduction, we expect. When we are reducing here at the top of the peak, you're at the highest rate of removal of the sulfur that we interested in. You expect then, when you remove this during an hour, that you have removed the whole peak, of course. That's sure. And also here, at about 750K during 1 hour we reduced, and then we hoped that we would have removed all the green sulfurs, and to see what is there left. Okay, now then one more TPR figure, and then I come to spectrum. I discussed 3 molybdenum catalysts. These, the loading is given as 2.2, that means 2.2 atoms per square nanometer, and that will be about 70% of a monolayer. Half the loading and half the loading. If you look to those, I'll give the results of these 3 catalysts. When you look to the TPR, I've only here given the first part of it. But of course, the thermodynamic part is of course not interesting. You see a little bit, these sorts of H2S is not important. You see here neatly the low temperature reactive sulfur. You see the reactive sulfur is more reactive the higher the molybdenum loading. That makes you of course optimistic, because the turnover frequency goes in the same way. And we find indeed that we have a nice correlation for molybdenum alumina between the peak temperature and the activity. Okay, and then the spectra. So the CO spectra, CO can be solved on alumina. We start with, of course, we first start with the alumina itself. We have given alumina the same treatment. So we have sulfided it and then heated it in hydrogen to 423K, 770K, and then we can compare it. Now what you find is that we see 2 sides on alumina. The CAS are Al3 plus sides that absorb H2S very strongly. You see you have to go to higher temperature to remove H2S so that you can see it. And you also see the hydrogen bonded CO here, and you see that at 423K reduction is sufficient to free them completely from H2S. So what you see here are 2 things that, yeah, that's fantastic. Thanks. What you see are 2 things. So you see here that after sulfiding, all the sides of alumina in this case are blocked. We didn't flush too well, obviously. And then when you heat at 420K, you see a spectrum. 770K, you see that this peak increases, and this is CO, again absorbs an Al3 plus. And obviously you have to go to high temperature to free them from adsorbed H2S. When you heat the vacuum, you find the same. When we do the same for molybdenum alumina, and I take first a sulfided case, and what you see when you increase the CO pressure in the cell from 5 to 75 millibar, what you see is a red peak that's new, and you see here the alumina peak, and perhaps a little bit fish-salt CO. But a red peak, of course, is important. You see in all spectra, you see blue peaks because of the alumina. They should be there. It's even a way of seeing what you've done with the sample. It's an internal calibration. And we believe that this is molybdenum 2 plus. Why molybdenum 2 plus? Of course, when you have more back donation, you expect that when you have molybdenum 2 plus compared to 6 plus, you have more extensive back donation, you expect it goes to lower frequencies. And also there's a lot of literature. We expect that molybdenum 2 plus is here, and molybdenum 6 plus and 4 plus is about here. So we see here some adsorption of CO molybdenum 2+, but not much. When we reduce the same catalyst, then at 453 K, it changes completely. We have now a much more intense molybdenum 2+ signal, CO adsorbed molybdenum 2+. And you see that it's very strong, the adsorption doesn't change. Already at 5 millibar, all the sites are filled. You see also here an intriguing peak at 2060. You've given it a lot of attention, and in literature there are people, it has been suggested that's molybdenum 0. We don't believe that's molybdenum metal in this system. We think it's also molybdenum 2+, but that we have here the edge sites and here the corner sites. And the idea then is that, and when you want to have more details, there's a good co-author in the audience. The idea is that at the corners you have more space available, so you have a better, a more intense adsorption CO, more overlap of the bonds, and so it goes to lower frequency. It's a suggested tentative interpretation, I would say. When we go to higher temperature, there doesn't change too much, except the 2060 band disappears. So that would then mean in our terminology that you see there some restructuring of the molybdenum sulfide slabs. When I summarized it, then you see here only the 75 millibar sample. By the way, everything is being done at 70 K because adsorptive CO are weak. You have to go to very low temperature, of course. And then you see what they said. You have a weak adsorption at low temperature. Also, this is nice in agreement with TPR, of course. At 353 K, nothing should have happened. You see the system is the same. So it completely is in agreement with TPR. And then at 453, you indeed see suddenly a big peak. So we think that this proves that we have here, we are measuring here the sites responsible for the chemosorption of that sulfur that we called SX, and so it is. We call it now sulfur adsorbed on edges and corners, of course, and with a 2+, we guess. When we go a little bit higher temperature to 110 K, and you see chemosorption, you see that all the intensity are a little bit lower, and the alumina intensity have disappeared. You see that these are much more stable chemosorption on alumina, what you expect, of course. And you see nicely back here that you have here this peak at low temperature. After restructuring, it has essentially disappeared. We will not be satisfied with the conclusion because you will have seen at 773 K you don't see so much difference with the lower temperature. I lost a little bit of time. Finished. And we took different spectra, and what we did do, we looked to the spectra taken at 75 millibar and 25, and we took the difference. And then we hoped that the molybdenum 4+, that's a little bit weaker, and so obviously we could see it. And then we have some indications that we see it. This could be the molybdenum 4+ 2180. In fact, the alumina, here is the alumina 3+ in principle, and that's of course it's just in between the two alumina contributions. So it's difficult to see, but anyway, we have also a little bit some other spectra of other systems at other conditions. We find indeed at a high temperature some more evidence from molybdenum 4+. So although you don't see it too clear, we believe we have sufficient indication to believe we have it. Now then two last spectra. Maybe I take a lower loading. Basically we see the same, we see more alumina, of course you have more, and you see again that the molybdenum 2+ comes, and that you see here the restructuring go up to a high temperature. Now I'll skip the lowest loading, and then Mr. Chair, I come to conclusions. I'm just in time. What are the conclusions? Now we think TPS combined with TPR, that gives a lot of information. The sulfur we have is adsorbed H2S Non-stoichiometric sulfur, SX, or sulfur can be solved on edges and corners, SH groups. The stoichiometric sulfur is not relevant in HDS. The infrared spectroscopy gives us information. I didn't stress that. Pre-treatment is of course crucial. When you don't have the right pre-treatment, you see nothing with this technique of chemisorption. You have to make the exercise before you can use chemisorption, of course. It's strongly adsorbed on aluminum. The TPSR patterns have been further resolved. We believe now that SX is indeed chemisorped sulfur on molybdenum 2 plus edges and corners. And that we probably have molybdenum 4 plus from S and H groups. I didn't go in detail, you also could come up with a little bit different chemistry there. And we see morphological changes. And the separate aim was HCO and usual molecule, we think it's very suitable for this type of calculation of powerful technique. Thanks.
Thank you very much, and thank you for bearing and improvising with the audio-visual facilities. So this talk is now open for discussion and comments.
Everybody sees MO4 plus by XPS.
Yeah.
On what basis do you think you have 2 plus? For what reasons? I mean, this is quite a departure.
Yeah, that's of course that we want to content new things, of course. When you do XPS, molybdenum 4 plus by far the most extensively present ion, of course, because all the molybdenum you see is, of course, nearly everything is molybdenum 4 plus. When you take such a cluster, it's not the best drawing for it, but nearly everything is molybdenum, this is the black and molybdenum, everything molybdenum 4 plus. You have only a few molybdenum 2 plus, and at the edges, why not? So, and an XPS, of course, the molybdenum 2 plus is just in between the 4 plus and the sulfur. And when I did XPS, so that's a little bit, some years ago, the machines were, of course, a little bit less advanced than now, but it was, for me, it was impossible to see it, to be completely sure, because it's a minority. We did not yet quantify it. We should do it. We can do it. How much molybdenum 2 plus we have. But it will, of course, you have much more molybdenum 4 plus. So the strange thing is, in XPS, you have so much of the QC here that it's not such a useful, it's easy technique to find this. So we think it's consistent.
Okay, we have time for maybe 2 more questions. I see Dr. Clausen is mine.
Yeah, I wonder why your peak corresponding to the SX is so sharp, whereas your peak corresponding to the SH groups are so broad.
Yeah.
It extends over maybe 300
Yeah.
K. Why is that?
No, it's a good question. It's also surprised us that the SX was so sharp. We had much broader, we had expect much broader signals. The SH, of course, it certainly does H2, there's hydrogen atoms out there around. So you can make H2S without adding hydrogen. So it's also not thermodynamic sulfur, so it should also be at the corners. I really don't know. It has also surprised us. I think it's a very fundamental question. We had hoped that we could see more of it. Perhaps we go back to it and try to find it. The SX obviously is very well defined, and the SH not. But so it's not a good answer, but we don't know. I would be interested for the suggestion.
Can you say something about the acidity of the sites from the CO adsorption, the CO infrared information?
We did not see that, I guess. I think we did not see it.
Well,
perhaps you can help with that.
Polynated unsaturated scientific. I mean, it's just a molybdenum carbon or carbon monoxide complex, and we made previously capabilities
Yeah, you could take another molecule. Yeah.
Can I maybe ask a very quick question? And It's known that you can have different types of molybdenum structures, just like the CoMoS, you have the CoMoS 1, CoMoS 2.
Yeah.
In some of your earlier work with Bob Scheffer,
Yeah.
you showed that if you calcine these catalysts to very high temperatures, you
Yeah.
would see the type 2 MoS2.
Sure.
My question is, have you done the CO to see if there's a shift indeed between these two types of molybdenum
That's
structures?
something we want to do. We did not do it yet. But certainly, what we found, we could never find the technique that you saw something. So now I would like to repeat now that and to check it.
Well, thank you. Thank you again.